This is lecture 4 for 214. It is Thursday, February 2nd. All right, what we need to do is we need to have a little bit of story time, a little bit more of physical science, because as I lecture, I listen to people talking amongst each other, thinking about what they're going to do later after class. But the other thing I do pay attention to is when I communicate to you what's going on in class, inevitably about 50% of the class just sits there and I have no idea. The other half of the class turns to that half and goes, don't worry, I got this. On Tuesday, I'm sitting there listening to class, and that 50% of I have no idea starts creeping up. 60, 70, 75, and then I start realizing I could have a full-blown just academic riot on my hands. So I have to take the time to communicate because there's some things that we need to really get a firm grasp of. If you have a charge and you have another charge and you have another charge, you need to visualize the forces and what goes on. And so what I'm going to ask for is, what's the sum of the forces for charge 1? And so the forces on this charge I will have as red. So positive, negative, dissimilar charges attract, similar charges or same polarity charges repulse. So this gets attracted to that. And so this is a line representing the path from one charge to another. So it feels a force in that direction. Here, they are the same charge, so they repulse. So there is the little line connecting the two, and then that is the force line. And what in the test, just like in these problem sets, there's going to be a problem where, given a set of charges, sum up the forces and give me the resultant. So what you have to do is, yes? I'd have to specifically define, yeah, so I would say some of the forces on 1. I could ask some of the forces on 2 or 3, it doesn't really matter. Now, the magnitudes of these come from Coulomb's law. So that F is K, first charge, second charge, distance between the two. Just the number. Direction, logic, and trig. And so what's going to happen tomorrow in tutorial is that we're going to do a few more examples of vector addition with forces and E fields and all that stuff. And we should get something if we do the tip to tail method or the parallelogram method. You would get a sum of the forces that looks like this. And that is the basis of the first problem on a test. The other thing we moved on to was electric fields. And once again, the electric field, it is written as a magnitude and is simply kq over r squared. So when you're using Coulomb's law, you have two charges at least. In electric fields, you can have just one. But for electric fields, you frequently ask, well, what's the electric field vector at that point? And what you do is you think about the charges and what those charges do with regards to their electric fields. Positive charges radiate their electric field lines. Negative charges, or they radiate outward. Negative charges, their electric fields radiate inward. So when you're saying, what is the electric field at this point from these three charges, this one sees the electric field from this charge, and it is radiating inward. So you draw the arrow like that. The positive charges radiate outward. So in this case, it's like this. And you need to pay attention for all of these and just kind of keep track of where those lines are. And then for one, its electric field line radiates outward as well. So those are the electric field lines. And what you would do, like with these magnitudes, is the sum of these electric field vector lines, you would do the tail to tip method and you would get something like bigger like this. And that would be the sum of the forces. And it really does require logic and trig. That's the important part. The big mistake that many students make is they're not quite, they fall into the trap of, well, there's only one way to do this, and it's got to be a particular way. However, let's do some more studies. Let's say we had a positive charge and a positive charge, and down here we have a negative charge and a positive charge. And we have 3 points to study. The red will be whatever the charge is on the left. So this red charge is a positive charge, which means that the E field radiates away from this positive charge. So here, the E field heads left. Over here and here, since it's radiating to the right, looks like this. So you have the E field looking completely opposite from one charge. It's all based on its relationship to the point that we're studying. So for this positive charge on the right, if you're to the right of the positive charge, you're again have an E field to the right. But to the left of the positive charge, the E fields go to the left. Now let's do the same thing for this. Positive, positive, so its charges look the same. They're radiating outward. But this negative charge, it radiates inward. So its electric field lines look like that. So now let me number the points. which of these points is it possible that they add up to 0, that the vectors add up to be nothing? 2, 4, and 6 can add up to be 0. Why? They're the opposite direction. Now granted, we don't really know the magnitudes of these things. All I'm interested in is identifying the possibility that it could be 0. So where the vectors are opposing, such as 2, 4, and 6, those would be the regions where you would study. If I ask the question, where between these points is the electric field 0, you wouldn't bother with 1 and 3 on the top, and you wouldn't bother with number 5 in the middle, because it's impossible. Positive plus positive will still give you a positive. Is there a way that you can take a positive and get 0? No, you can't do it. Just like negative plus negative will never give you 0. It will continue to give a negative value. So you need to understand, there will be problems where I go, where's the E field is 0, and you're looking at 5, trying to figure out where along 5 is the field 0, and then I know you don't understand what you're doing. So it requires logic on your part. All right. Now, with one of the things that were mystifying people was the whole idea of, yes.
I get like the one before that, like with the 3 points, like that, but I don't understand how, like you're getting arrows for, like, the guy.
You mean for the ones on the left?
Yeah.
Oh, the ones on the left are not force vectors. Let me be clear about this. They are electric field vectors. So, when you have that negative symbol, its electric field lines are going towards. So at that point, in. At that point, in. At that point, in. For this positive charge over here, it radiates outward. So at this point, to the right. At that point, to the left. At that point, to the left. It does apply for all the points because the electric field line for a charge goes on effectively forever. Now, one of the things that we've been looking at is if you have a positive charge here, obviously the electric field line at a particular point goes to the left. So if I placed a positive charge here, does it accelerate to the left or to the right? It goes up. Well, okay, what I'm really doing is I'm putting the particle right there. So it goes to the left. I'm still working 1D motion here. So let's not get 2D. If it was up here, obviously it would go up and to the left because the E field is that way. The E field is related to Coulomb's law Because if you took that charge that we're studying, let's say that that was little q, and then this was big Q. We could factor out that little q, and we would get the electric field. So it's not truly necessary to know what that charge, this charge is. What is necessary is to know what the electric field is. Because, as an example, if the E field points to the left, and why would it face to the left? Because if there was a big positive charge over here, and you put your positive charge here, obviously the force would be to the left.
I think I'm slightly confused on the page that we read. Why you take 3 points and 4 lines? Not that page, but the one after that one. Like,
This one.
right, you have E1 and 3.
This is E1 from that charge.
Right.
That is E2 to that charge. That is E3 from that charge. That is the sum of the E fields. The fourth line, that extra line, is the sum. Yes. Just as up here, there's a force line from 3 on 1. There's a force line on 1 from 2. So that one and that one, you sum them together to get the extra line, which is the sum. Yes? In the way that this particle behaves, say I had an E field at that point because there was a positive charge there, and then what I did is I made the charge invisible, and I only told you that the E field line was headed to the left. The force on a positive charge would be going to the left, because positive charges always feel forces in the direction of the E field line. So when I say, and this is kind of an analogy, if I have a charge here and I tell you that the E field line is to the left, you know that there will be a force line to the left because the E field line is there. If it makes you feel more comfortable, you can kind of think of this what would create an E field line to the left? A positive charge right over there. And then you would understand positive charges repulse, and then it moves in that particular direction. And so if that's what you got to do, then that's what you got to do.
So if that negative way go.
You could actually envision, oh, and if it was a negative charge, the E field line is still to the left, and negative charges always move in the opposite direction of the E field. So if you know what the we're kind of moving towards capacitors. If you know where the E field is, if I give you the E field, you don't really want to know anything about the source charge that created it. If I give you the E field, you know that negative charges move in the opposite direction and positive charges move in the direction. So what I'm trying, really all this is now is physical science. Just doing the English. Yes?
Where the E field points to the left. And then points towards the.
I declared it was to the left. I just said, I'm giving you a problem. You're a charge in the room. The electric field is to the left. Your positive charge, which way do you go? You don't have to have that charge outside the dotted box. You can just be told that's the charge. If this room was the or in this room, I could say that the E field line is that direction. So if I let go of a positive charge, it moves outward into the classroom. If it's a negative charge, it moves towards me. So it's all really what I'm trying to do, and this is the big difference between 214 and 213. Visualization. Being able to see electric field lines and what they mean. And it's a big step in this class.
So does the force always follow the electric field line? Is that the way it works?
The force, it depends on the charge. Let's say in an instance, this room, the electric field line is that way. Why? Because I say so. Positive charge, it will feel a force in that direction of the electric field line. If it was a negative charge, it would feel a force in the opposite. So positive charges feel forces in the direction of the electric field line. Negative charges feel forces in the opposite direction. Oh, don't mind me. So, one of the things that we will be doing is kind of what I'm doing is I'm drawing the symbol for, or drawing a representation of a room where on one side it's positive, on the other side it's negative. Rooms like this have consistent E-field vectors. Now, this is a grotesque version of a capacitor. They're way smaller and different shapes and stuff like that. But when you have a room like this, the electric field vector, regardless of where you are in the room, is the same length and the same direction. Now, when you do the electric field vectors for this in lab, you'll see that it's consistent between the plates, but as you get further away from the plates, they start doing weird stuff like this. In class, we won't venture into this area. We'll stay in the safety of this. And let's say that the distance between those 2 points is 3 meters. Now, in electrostatics, or in the electrostatics lab, only the negative charges move. Positive charges do not move in the electrostatics lab. Yes, little bits of fluff off the rabbit fur do move, and yes, they do contain positive charges. But in terms of the effects that you're studying, it's the negative charge that's actually doing the moving. In 214, we're dealing with positive and negative charges both can move. So when I say you have a positive charge with a particular mass and a particular charge, it's okay. I had someone ask me yesterday about why is the charge positive? Why is it moving? Because positive charges don't move. Now that we're outside of electrostatics, positive charges in reality can move. Yes.
So, okay, these positive and negative. So, like the negative, are we supposed to be thinking of it like it's like an electron or something like?
Yeah.
It's not like a nucleus and it's like
Yeah,
a transference of electrons.
Really, these are like pieces of metal.
Say
There's-
if I had a balloon and I rubbed it on my hair or something and I like stuck it up there, am I supposed to be thinking of it like, okay, the electrons from my hair or something stuck to the wall?
What happened? Yeah, and that actually, I think it's a question in the lab. We can talk about that right now. When you rub your hair on a balloon, the electrons on the balloon come from your head and it spreads all over the balloon. When it gets close to the wall, the electrons in the wall move away. They go deeper into the wall. So really what you have is you have a polarized region of the wall where the wall is positive and the balloon is negative. Dislike charges attract, so they stick. And you can leave it there.
Okay, and it'll eventually like neutralize.
Eventually it will neutralize because eventually the electrons will slowly start moving over. Rubber is a insulator and drywall is an insulator. So it attempts to prevent the electron transfer, but it does gradually happen. But initially that balloon will stick to the wall. What we're going to do is we're going to put this positive 20 gram, 40 microcoulomb charge right here, and the initial velocity is equal to 0. And I'm going to ask myself, well, what's the velocity? What's the velocity here? How long did it take to move over? And really what we have done is we're studying a one-dimensional motion problem. This charge, let me write this stuff down. This charge is experiencing a force. The electric field is to the left. The force is to the left as well because it's a positive charge and the electric field goes to the left. When you've got capacitor or plates like this, the electric field lines always run from the positive plate to the negative plate. So it feels a force. The force on that charge is related to the electric field. And I'm going to need to give you the electric field magnitude, 40 newtons per coulomb. Newton's second law says the force is equal to ma. So you could say that QE is equal to ma, or QE over m is equal to a. You can put those two things together. Now, one of the reasons why we work in regions like this is we either have to do something else that we're going to get to eventually, or if I make this anything more complex than this, we have to use calculus. So we have to keep that E field unchanging.
Does that say 40 newtons per coulomb?
40 newtons per coulomb, yes. Now, it is a one-dimensional motion problem, so we have to go through all of the basics of solving for a one-dimensional motion problem. You set an origin, which typically is the starting position. You set up a positive and a negative side. The way that this problem is set up, all the motion is to the left. So since I'm not a fan of negative signs, I'm going to put negative to the right and positive to the left. With one-dimensional motion problems, you can do this quite easily. And in many cases, it simplifies the problem. In 2D motion, don't do that. Up is positive, down's negative, left's negative, right's positive. Keep it consistent. But for 1D, you can kind of get away with it if you announce it. It's a 1D motion problem. And then we do what we've always been doing. Next, we identify, well, really what we do, we identify 0 first. Like I've said before, I don't like numbers. And then a student challenged me by saying, you do have a favorite number, it's 0. Because 0 gets rid of the unnecessary fluff in the problem. So what values are 0? The initial position, so x naught is 0, v naught is 0. And I said so. I said over here that the initial velocity was 0. That would be something I'd have to give to you. Do I know the final position? Yes. The final position is at the other end of the capacitor, which is 3 meters across. So we do know this. Do I know the time? No. Do I know acceleration? Not quite yet. Do I know final velocity? No. Do I know time? No. Do I know A? That was not given to you numerically. So I got a lot of problems. I got 3 equations over here that are unknown, or 3 variables over here that are unknown. I got 2 over here that are unknown. But the one thing that I do know is that acceleration is QE over M. Do I know the charge? Yes. Do I know the electric field? Yes. I know the mass, yes. So what I'm going to do is substitute this into that. One of the lessons about problem solving, if at first you can't identify it, see if you're able to substitute in something else that you can identify. So x equals 1/2 QE over M t squared. Everything is a known quantity now except for time. Solve for time. 2mx over QE is equal to time squared. So time 2mx over QE. So that ends up with the square root of 20 times 10 to the negative 3. Remember that the numbers that you plug in, their units must be in the form of kilograms, meters, and seconds. X, 3. Q, 40. E, 40. So that 40 cancels out with that 40. And I'm left with Where is my... Oh, there it is. Oh, that number turned out kind of nice. So it came out to be 8.66 seconds that it would take to go across. Now that t is a known quantity and we effectively know what a is, let's get a if I asked for the acceleration. That would be 40 times 10 to the negative 6. 40 divided by 20 times 10 to the negative 3. So that would mean that the acceleration would be 0.08 meters per second squared, exact. So our final velocity is 0.08. The time is 8.66. And we get a velocity of 0.69. Now let's just write it out in full. 0.6928 meters per second. So in situations like this, what we're doing is we're taking experiences, problems that we've done before in 213, and we're adding an extra layer. Rather than the particle having a rocket causing it to accelerate at 0.08 meters per second, we're now putting it in an electric field so that it will accelerate at the same rate and we can get some motion out of it. It's similar to the one that we did earlier where the charge moved over from a particular height at rest. Everything that we did used the motion equations, and the fact that F is equal to ma and that F is also equal to QE. And so those are the basis for a lot of the motion problems that we have in the problem set. Now, the third equation, major equation that we're using, we've got Coulomb's law, F, K, Q1, Q2 over R squared. We have electric field. E, K, Q over R squared. We have that these are always positive. And then we have the idea of potential. And its potential, big V, K, little q, R. Now it is intentional that I'm writing little q over R. In the real world, you have hills and valleys. Not vales, valleys. And with the hill and a valley, you know that if you put a little pebble on the hill, these things always go downhill. Pebbles look for lowest potential. So currently we're only thinking about potential in terms of gravity right now. With something like this, just as you need to have an origin for like two-dimensional motion and stuff like that, you need to have a reference point so this is the reference altitude, and we commonly refer to this as sea level. Sea level is like the base level for the planet. If you're above sea level, you've got a positive altitude. If you're below sea level, you have a negative altitude. Everyone's very familiar. Right now, Oxford, Mississippi, I believe, is about 500 to 700 feet above sea level. Why is Denver called the Mile High City? Because it is literally a mile above sea level. Mexico City is about 7,500 feet above sea level. You've got places like Machu Picchu and Mount Everest, which were even higher. Below sea level, well, you could go scuba diving. You're now below sea level. Other places are below sea. What?
I said, or you could go to Louisiana.
Or you could go to Louisiana. That is true. The majority of New Orleans is below sea level. With the French Quarter is like the only place. I mean, why are there cemeteries? All the bodies are above ground. Because if they dug, they would hit water. Death Valley, below the Dead Sea, all below sea level. And so there are examples where it's below the reference point. We'll talk later about how they figured where sea level is on Mars, because it has no sea. But you do need a reference point. Now, the analogy that I used, I'm going to draw this, and the vertical is potential. And this is where you gotta just have an open mind. High potential, positive charges. Low potential, negative charges. Here in Coulomb's law, positive and negative, only the positives are allowed. For potential, draw a line. Potential can be positive or negative. So potential, it could be positive, it could be negative. If you're really close to a positive charge, this one has a potential that is greater than 0. If you're close to a negative charge, you have a potential that's less than 0. And once again, you also need to come up with a reference potential, and we need to introduce a new word. This reference potential, just as we say sea level is the reference potential for altitude, ground is the reference potential for the quantity of potential. And this potential of ground is 0. Now, let's do some simple examples. You are here.
V stand for voltage.
Yeah, V does stand for voltage. The units, and actually, now that we're into this, Coulomb's law, unit, newtons. Electric field, newtons per coulomb. Unit for potential. Now, there is another way to express it, but for right now, we're just going to use volts. I mean, volts like Newton, kilogram meter per second per second. Volt is short for something else, and we could figure that out, but not right now. The thing that we need to, now that I'm still looking at this, if we had a positive charge, positive seeks lowest potential. So this charge will want to go that way, that charge will want to go that way, this positive charge will want to go that way. And we have a consistent understanding of this. Rocks go downhill. Negative seeks highest potential. So if you have a negative charge, it will want to go uphill. Now, we're all familiar with just regular mass. Regular mass attracts all other forms of mass. In this type of situation, we almost have, you could talk about anti-mass, anti-gravity, gravity that behaves in a freakish way. That's what electric charges do. They introduce the idea of the opposite charge, something that behaves in an opposite way than what we're used to. So you are here, and you are 5 millimeters away from a positive 10 microcoulomb charge, and you are 8 millimeters away from a negative 5 microcoulomb charge. What is the potential at that point? And in the first parts, when we were talking about forces in Coulomb's law, when we were talking about electric fields, electric fields construct the electric field vector. Coulomb's law construct the force vector potential construct V. Where's the vector symbol on top of V? There is no vector symbol on top of V. Unlike electric field and the force field vectors, V is a scalar. It's a number. It could be positive, could be negative. It doesn't care. There's no direction involved with potential. All that matters with respect to the geometry is to get these R's as quickly as humanly possible. If I did angles and stuff, it would only be so that you could calculate these. The total potential V1 and V2. You're telling me that all I got to do is just add them up? Yes. Well, that seems too easy, too good to be true. No, honestly, I'm serious about this. All you've got to do is add it up. KQ1 over R1 plus KQ2 over R2. I'm going to 9 times 10 to the 9th. Q1 10 times 10 to the negative 6 over 5 times 10 to the negative 3. And we don't even square it. KQ2, 9 times 10 to the negative 9. Q2, it is negative. Negative 5 times 10 to the negative 6. And its distance, 8 times 10 to the negative 3. Oh boy. Okay, thank you. I get 1.24 times 10 to the 7th volts. So that's the potential. So that potential is great, so it is a positive value. It could be negative, but the way that the numbers worked out, it didn't come out that way.
For the K constant, is it positive or negative?
Oh, it is positive 9, but I think I'm still right. Yes, I still get that. That was a typo. Calculator, lady. We asked.
I had a different number.
Hold on. Uh-oh, we have disagreement. I have high confidence in my number.
I got it now.
Okay, so we get that. So this is the value. When you look at a problem like this, let's talk about it in ways that it really matters. Could something like this be on the test? Yes. It would be more like it would have to be a very simple multiple choice question. It could definitely be an appetizer question. Will it be on this test? I have no idea. The test is like 3 weeks away. But what I am saying is, when you see a problem like this, a lot of you will get distracted by, oh, what about the orientation, all the angles? Is it first, second quadrant? No. Potential is a scalar. You should just start having little bits of drool go down your chin, because I mean, you could drop your water bottle if you have stuff like that happen. But the bottom line is, it is an easy thing to do. You just add it up. And I'm serious, it is that simple. I think we're done. Quick announcements. If when in doubt, check your roll sheet or check your schedule. Make sure you are in this course. If not, you must see me today. Tutorial tomorrow, here, 2:30. There will be a tutorial. We'll go over homework and stuff.
Did we just check Blackboard to see if we're in?
Check Blackboard for what?